Hi there. In this video, we're going to be looking at how we do our gas law calculations. So in this first question, we are told that a balloon occupies a volume of 7.75 liters at a pressure of 125 kPa. Determine the new volume if the pressure changes to 100 kPa. Okay, so I always set up my initials, my ones on the left, and my final conditions, my twos on the right. We don't have to use GRASS method in grade 11. However, we still have to organize all of our math properly, making sure that whoever's marking our work can follow it. Okay, so I have my initial volume V1 at 7.75 liters, my initial pressure P1 at 125 kPa. My final pressure is 100 kPa. Okay, and we're counting all three of these as being significant digits like we do in our chemistry course. So I've just put the decimal after to make sure that we know all three are significant. And we're looking for V2, so that's our question mark. Okay, so our formula that we're going to use is P1V1 equals P2V2. We rearrange to look for V2. So if I'm looking for V2, I'm going to get rid of this P2. It's being multiplied. I'm going to put it to the other side. So P1, V1 divided by P2. Sometimes what I'll do is I'll actually circle what it is that I'm trying to find. That way I know I need to leave that alone and I need to move the other thing that's with it to the other side. All right, so once I have my rearranged equation, V2 is equal to 125 times 7.75 divided by 100. You'll notice that my kPa's cancel out. I'm left with liters. My final answer, V2 equals 9.69 liters to three significant figures. I'm going to put in a nice box so that the person that's marking it is able to follow my work and find the final answer. I don't need a statement as long as I have this box so it's easy to find. Great, so now my next question, at 100 degrees Celsius, a gas exerts a pressure of 250 kPa, again, all three significant figures. If the gas is cooled to 25 degrees Celsius, what will the new pressure of the gas be? All right, so here I have my initial temperature, T1 is 100 degrees Celsius. My initial pressure, P1, is 250 kPa, okay? My initial temperature is in degrees Celsius. We cannot work in degrees Celsius with these formulas. We must convert to Kelvin, so adding 273 to the 100 gives me 373 Kelvin. My final temperature, T2, is 25 degrees Celsius, which we have to add 273 to get it into Kelvin. That gives us 298 Kelvin. And I'm looking for my final pressure, P2. So my formula that I'm using is P1 over T1 equals P2 over T2. Okay, so again, I have to figure out what it is that I want to find, and that's what I'm going to isolate. So I'm looking for P2, so here's P2. The T2 is being divided. I need to get rid of this T2, so if it's being divided, to get it to the other side, I'm going to multiply it up. So P1 times T2 over T1. I'm just moving the other thing that I want to get rid of to the other side by doing the opposite. So the opposite of division is multiplication, so I'm multiplying it to the other side. So here's my new formula. Now I'm going to plug in 250 kPa times 298 Kelvin over 373 Kelvin gives me 200 kPa to three significant figures. So a better way of actually expressing that is 2.00 times 10 to the 2 kPa. Now I have a bubble of methane gas, CH4, is released from a deep bog. The temperature at the bottom of the bog is 12 degrees Celsius with a pressure of 375 kPa. If the bubble has a volume of 475 milliliters at the bottom, what will its new volume be just underneath the surface of the bog water level if the outside temperature is 35 degrees Celsius and the pressure is 99.5 kPa? All right, so in this question, I'm given an initial temperature of 12 degrees Celsius. I'm given an initial pressure of 375 kPa. Again, my degrees Celsius, I've added 273 to get that into Kelvin. I'm given an initial volume of 475 milliliters. Now, my final temperature is 35 degrees Celsius, which has to be converted to Kelvin by adding 273. My final pressure is 99.5 kPa. I'm looking for V2, my final volume. Now I need the combined gas law, P1 V1 over T1 equals P2 V2 over T2. I'm looking for my V2. So I have to get rid of the T2. It's going to go to the other side. It's being divided, so it's going to get multiplied up to the other side. I have to get rid of my P2. It's being multiplied, so it's going to be divided to the other side. Right? So this guy is coming down here to get rid of. This guy is going up here to get rid of. And then my V2 is going to be by itself. So my new formula is V2 equals P1 V1 T2 over T1 P2. So then I plug everything in, 375 kPa times 475 milliliters times 308 Kelvin divided by 285 Kelvin times 99.5 kPa. You'll notice my kPa cancels out, my Kelvin cancels out, I'm left with milliliters, which is what I want. It's a volume, so it has to be either liters or milliliters. And to 3 significant digits, 1.93 times 10 to the 3 milliliters. And then also here, I just want to point out that you can either use brackets, so bracket 375 times 475 times 308, bracket divided by bracket 285 times 99.5 bracket, or if you don't want to use brackets at all, the way that you would punch this into your calculator is 375 times 475 times 308 divided by 285 divided by 99.5. Because I'm taking all this, I'm dividing it by this, and then I'm dividing it by this after. Okay, and that prevents me from having to use any brackets. And you should get this as your answer. Okay, so finally, we're just going to look at a question that we're going to be seeing in chapter 12, but we might as well have a look at it now. Determine the volume occupied by 3.45 grams of carbon dioxide gas at STP. So there's a couple of important things here, okay? One is that they're asking us for STP. Okay, so STP is standard temperature and pressure, which is something that we have to memorize. So standard temperature and pressure, the pressure is 101.3 kPa, the temperature is 273 Kelvin. Okay, now the mass that we're given is 3.45 grams. We're not given initial and final conditions. When we're just given conditions and it's not changing from one thing to another, we're not dealing with any of the laws that we've studied so far. We're dealing with the next law that we're going to be studying, which is the ideal gas law, PV equals nRT. And PV equals nRT, pressure times volume equals the number of moles times R, the gas constant, times the temperature. So rearranging this for volume, which is what we're looking for, V equals nRT over P. I'm going to put the P to the other side because it's being multiplied, dividing it on the other side. All right. I wasn't given a number of moles though. I was given a mass. So I'm going to use my good old calculations going from mass to moles or moles to mass. Always use the molar mass. So 3.45 grams times 1 mole for every 44.01 grams gives me 0.0784 moles. This is actually a long number, my calculator. I'm going to keep that full thing when I enter into the next part of the calculation. Even though I just record my 3 sig figs here, I keep my full number in my calculator, put that full number in here, times 8.314 kPa liters mole per Kelvin. That's my units for R. That's my number for R that I have to memorize, times the 273 Kelvin, divided by the 101.3 kPa, plug all that in, and you will actually see that your units do work out here. If you keep your correct units for your gas constant, you will see that they actually work. So you get your moles cancel out, your Kelvin cancels out, your kPa cancels out, and you're left with liters, 1.76 liters. Again, PV equals nRT, the ideal gas equation that's coming up in the next part. Thanks guys, see you next time.